tarde, vamos dar início a mais um colóquio do IFGW. Então, antes de começar, eu gostaria de lembrá-los que o colóquio está sendo gravado. Então, todo mundo que se manifestar durante o colóquio está dando a sua autorização para ter o direito tanto de voz quanto de imagem. Então, hoje é com grande prazer que a gente tem o Marcelo França Santos conosco. Então, o Marcelo tem trabalhado em ótica quântica, fundamentos de mecânica quântica e sistemas de quântica aberta já há bastante tempo. Ele fez a graduação aqui na Unicamp, fez depois o mestrado e doutorado na UFRJ, um posterior pós-doc na USP, no Imperial College e depois na UFMG, onde ele foi professor adjunto. Inclusive, enquanto ele era professor lá, eu também estava fazendo a graduação lá na UFMG, por coincidência. Depois ele foi para a UFRJ, e dentro da UFRJ ele tem liderado o grupo de ótica quântica e informação quântica da UFRJ. E é importante lembrar que ele foi um dos responsáveis pela Escola de Informação Quântica de Paraty, que já formou vários estudantes nessa área e tem uma atuação bastante importante. Então, Marcelo, grande prazer estar aqui conosco.
Well, I'll speak in English because I know that there is at least one person here that doesn't follow Portuguese that well, right? So yes. So then, for everybody else, English is okay, right? Since I'm not a native speaker, then it's even easier to understand. The other thing that I wanted to say before starting, well, first of all, I'd like to thank. Actually, I forgot I should speak here. You see, it doesn't make that much difference, but still. I'd like to thank the organizers of the colloquium for inviting me. It's a great pleasure to be here, and I've written a short paper that was published a couple of months ago on the short summary of the history of quantum optics in Brazil. And actually, I've written it in the first person, so I wrote kind of my personal version of it. And my personal version of it started here, in this room. In May, probably May, or April or May, I think May 1994, when Luis Davidovich was invited to give a colloquium here, and I was in my fourth year of the undergrad studies, and I came to watch his colloquium, and I figured that quantum optics was exactly what I wanted to do. So that's how I entered the field. So in that sense, it's a 31-year cycle that kind of completes itself today. It's the first time that I come back as an invited speaker for the colloquium here, so it's a 31 cycle finished today. So that said, I'm going to speak to you about entanglement from which process indeterminacy. And because this is a colloquium, I will talk a little bit about entanglement, its origins, how it goes on, and then I will try to convince you that what I'm going to tell you here is something new. Okay? And that's why it's interesting. Even though entanglement is an old topic. And obviously, I need to thank the supporters of this this research that I've been doing for a long time. And we've just started a new INCT of quantum devices. And you can find information here, including postdoc information. So I'm going to talk a little bit about this in the end. So let me start by saying that entanglement is an old topic in quantum physics. It's a topic that came around the 1930s, and Weil, I don't know how to pronounce, was one of the first ones to notice about it. Schrödinger's, obviously, people know about his observations regarding entanglement. And then you have the famous EPR, And then Schrödinger's cat and EPR are the most famous old examples about the discussion regarding entanglement. And basically, the idea concerning entanglement can be summarized in this observation by Weil in his book from 1931, which is the fact that, like in quantum systems composed of multiple interacting parts, the whole is greater than the sum of its parts. Okay? And another way to talk about entanglement, one that the easiest way from a mathematical point of view is to say that, like, if you have a composed quantum system, right? Anything that cannot be separated in something that is solely from one part and something that is solely from the other part is entangled. And if you think about it, like the state of possible, the set of possible states in a composed quantum system is much, much larger than states that can be separable into something that belongs only to one part and something that belongs only to the other part. Which means that, like, most quantum states are entangled. Like if you were to draw randomly one state, like, for example, I want to write a quantum state of a composed quantum system, and I'm going to draw the coefficients, okay, of my state. There is a chance that goes to 0 that you will draw a separable state. The same can be said about preparing it in the lab. It's basically impossible to prepare a state that is separable in the lab. Okay? Basically. It's as difficult as preparing a pure state in the lab. And actually, these two things are related. The fact that you cannot prepare a pure state in the lab necessarily means that what you are preparing, your system is entangled with something else. And entanglement also lies at the core of the coherence. It is the correlation that leads to the coherence. Okay? The coherence meaning the disruptive force, the disruptive act that makes a quantum system lose its capacity to display interference phenomena. And the coherence was actually the subject that led Amir to do his works and so on and so forth that we are celebrating this year, including the Nobel Prize that was one connected to his works as well. Amir is sitting here, so I think it's fair to mention this. All right, so this is like entanglement in a nutshell. And by the way, because I see that there are many students in the audience, if you have any questions, please interrupt me, okay? It's more important that you ask questions and you get your answers than for me to finish saying whatever I came here to say. So I'm going to focus on entangled photons, okay? So as I said, any quantum system, if it's composed of subsystems, it displays entanglement. You can find entanglement in it. It can entangle atoms, atomic states. It can entangle other bosons, for example, photons, and so on and so forth. But I'm going to focus on entangled photons. Okay? Why am I going to focus on entangled photons? The reason I'm going to focus on entangled photons is because, first of all, they are easy to produce in the lab. They are cheap to produce in the lab. They have been used for a while now to study many different aspects, and they even became commercial. Okay? And first of all, you can use entangled photons to win the Nobel Prize. That's what these guys have done. Okay? So Alain Aspect did it in the beginning of the 1980s. John Clauser did it in the middle of the 1970s, and Salinger did it in the middle of the 1990s and from then on, exactly. And they've produced and tested entangled pairs of photons, and they did it to show the famous Bell's inequalities, the violation of the famous Bell's inequalities that eventually led to the Nobel Prize in 2022. So you can use them to win the Nobel Prize. Well, they could, okay? I'm not sure if you can from now on. I'm not sure if they will give a second Nobel Prize to entangled photons, but who knows? Huh? maybe on quantum computation, who knows. But the fact is that you can use entangled photons to test quantum properties of light, to test fundamental properties of quantum physics like violation of Bell's inequalities. You can use it to simulate quantum dynamics and computation. You can use it to generate photons, to generate single photons, that you know that you have a single photon going somewhere, and this is already commercial, okay? For example, you can use it to generate polarization states of a single photon that are truly random. And then you do it in a way that you know that there is a photon with a randomized polarization state traveling in a certain direction, because you use the other pair, the one that is entangled to it, to certify that there is one traveling in one direction. You can use it for quantum cryptography, again, already commercial. You can use it for quantum sensors. This is becoming a reality now. And who knows, applications to biology, applications to neuroscience. I'm going to talk a little bit about it in the end. So you see that entangled photons are a very powerful tool nowadays, all the way from fundaments to commercial, to products, to devices. And when we talk about entanglement, as I said, the whole is greater than the sum of the parts. So, why? Because there has to be some loss of information. Okay? In this case, locally, in the sense of this, the subsystem, okay? Here, I don't necessarily mean locally in the sense of space, localized in space. I mean in terms of subsystems that are composing my whole system. Locally, there is less information, so there is some sort of indeterminacy, and you need this to have entanglement. So, for example, when we prepare entangled photon pairs in spontaneous parametric Dow conversion. Spontaneous parametric Dow conversion is a process, a nonlinear process in which I have a crystal, I shine light in this crystal of a certain frequency, and the crystal converts this light. It converts one photon from this beam into two photons of a smaller frequency, so that energy is conserved. So the sum of the two frequencies that are converted has to be the frequency of the photon that I'm destroying. And these guys can be generated in an entangled state. So, for example, if I have a type 2 SPDC conversion, I can generate photons that are entangled in polarization. You see that I cannot write this state as a product of something that belongs only to S, system S, and something that belongs to system I. There is no way to write this as a product of this. They are entangled. If I have a type 1 SPDC, which creates photons of the same polarization, but then I put two crystals like this, and this one produces H polarized photons, this one produces V polarized photons. If I somehow erase the information of which one created the given pair, again, I have entangled photon pairs, and again, I have loss of local information. And here, for example, I have, I erase the information in this beam splitter here, so I create the photons here, and I erase the information of where they were created. So, I mean, in all these situations, I'm losing local information somehow. However, it's important to say, it's always the same process that is creating the photons. And therefore it's creating the entanglement. So what I'm erasing is not information about which process created it, I'm erasing the information of where it was created or something like that, okay? Or the frequency, for example, or anyway, I'm erasing some type of information like this. And these are the examples of creation of photon pairs. Again, so I can generate biexcitons and then allow them to decay. And again, I'm I create photon pairs, entangled photon pairs, but again, I have reached decay indeterminacy, but it's a decay process, so it's the same process. Here, I can use fiber-based photon pair generation. In this case, I can erase either frequency information or polarization information. If I erase frequency, I generate pairs of entangled in polarization. If I erase polarization, I generate pairs entangled in frequency, but again, it's the same process, and so on and so forth. So you see that all these sources of entanglement, the indeterminacy is always something about when or where or in which color it was generated, but always the same process. Okay? And I need this indeterminacy for entanglement. So a while ago, something like 11 years ago, Ado Jordan from UFMG, who works on Raman interferometry and Raman spectroscopy, asked me, he said, there's something wrong with my system. I'm measuring temperature in two different ways and I'm getting different temperatures. And I told him, yeah, maybe I know why. It's probably because the photons that you are generating are correlated, and this correlation is changing the state of your system. Therefore, you're not measuring temperature anymore, because you're not in equilibrium anymore. And temperature has to do with equilibrium. So we started then a program 11 years ago of testing the properties of the photons that he was generating in his system, Raman scattering. And the big question was, are they entangled? So we started on trying to understand this, and this is a series of papers that tested correlation, but not necessarily entanglement. So we tested time correlation, we tested polarization correlation, but not entanglement. But the question remains, are they entangled? So I'm going to talk a little bit about this series of experiments and series and the development of the theory about it as well. So I've talked about entanglement, and because I'm going to talk about Raman scattering and Raman spectroscopy, I'm going to switch now to Raman and talk a little bit about it again in a way that I hope will be easy to understand for everybody. So let's talk about Raman, because I'm interested in Raman generated photons. So the picture that you see on the left is Raman himself showing his effect, well, by then not his effect obviously, showing some effect of light to a bunch of very surprised scientists. And what he was showing was that he was shining light of a certain color in water, and he was seeing light coming of a different color, a smaller frequency, out of the water. So he was somehow showing that light was converting, water was converting light from green to red. Okay, essentially this. Now, picture, he was doing it without lasers, without LEDs, okay? So this is how difficult it was to do experiments like this. And the process of this conversion is very ineffective. It's 10 to the minus 7, 10 to the minus 8. So that's the chance of converting one photon to another one, okay? So picture this done without a laser, okay? That's how difficult these guys had to work by then. But basically what he was showing was that in materials that are transparent, okay, there is still one scattering that is inelastic that can happen. And what happens is that a photon coming from your pump interacts with the material and loses energy to the material in the form of vibrations. So the material starts to vibrate. And therefore, the material gives back a photon of smaller energy and hence smaller frequency. It's an inelastic scattering of light. And the material can also give energy to the photon and convert it in a higher frequency. Okay? We are going to call the conversion to smaller frequency Stokes, the conversion to higher frequency anti-Stokes. Okay? But because The conversion to smaller frequency is spontaneous in the sense that even if the smaller frequency field is in the vacuum, it can happen. I don't need a vibration for it to happen. The signal from the Stokes side is much larger than the signal from the anti-Stokes side because the anti-Stokes requires a vibration in the material to happen. Okay? So that's basically the Raman scattering in a nutshell for you. And by the way, this picture is just to remind you that in fact, I'm generating pairs of photons in all the spectrum, in principle, as long as the sum of these guys, okay, adds to twice the sum of my pump. So that's just to remind you. I haven't explained pairs of photons yet, but it's just to remind you of that. So a semi-classical vision of it, picture of it. You pick up your material, can be your molecule, can be your crystal, and the atoms are around their equilibrium positions. And let's assume that I'm going to generate small displacements around this position, so I can approximate my potential by an harmonic oscillator. So I'm going to treat these vibrations as an harmonic oscillator, as long as the displacement is small. And I'm going to pick up the polarizability of the material, like the response of the material to some external force that is trying to polarize it. I'm going to expand it in terms of powers of this displacement. And if I keep just the first, so if this term gives me the refractive index of the material. The next term is enough for me to explain Raman scattering. So this is the natural frequency of oscillation around this potential for small displacements. And what I do is that when I shine some external electric field that is also oscillating at another given frequency, I induce a dipole in this material, and the induced dipole is of this type, and then I have the polarizability that oscillates in principle with the material's frequency. I have the field that oscillates with its frequency, and you see that, like, by simply picking up this formula for the polarizability for the induced dipole, I see that I'll have an oscillation of the field that is in the frequency of the field itself. So that's elastic Rayleigh scattering, and then I have oscillations that are in the difference and the sum of the oscillations of the field and that of the material. And that's a Stokes and anti-Stokes, but then obviously in a kind of classical way of talking about the vibrations and the fields. But because we want to talk about photons, phonons, and so on and so forth, we quantize this. And to quantize it, it's not that difficult. What I do is I pick up the interaction of this dipole, this polarizability, with the electric field. And here I'm going to quantize both. So I quantize my movement around the equilibrium. This is now quantized, the movement of the atoms around the equilibrium. And I quantize my field, my external field. Okay? So this is the quantization of the movement. So I turn my position, my relative position in respect to the equilibrium position, into operators that create and annihilate vibrations, and I quantize my field. And the quantization of my field, obviously it's multimode. I have fields in all frequencies. But just for the sake of explaining it in an easier way, I'm going to keep just 3 frequencies that are the ones that I need for now. And those are the pump frequency, this one, the laser, the Stokes frequency, the one that is smaller, and the anti-Stokes frequency, the one that is higher. So this is the 3 modes that are going to matter for me right now. Okay, just to explain what happens. So now everything is quantized, and if I remember, there is an electric field here, there's another one here. So the interaction Hamiltonian, taking everybody into account, is this one. And here I'm already doing an approximation, semi-classical approximation, which is the following. I'm going to treat Stokes and anti-Stokes as quantized fields, but the laser field I'm going to replace by a complex number, the operator, the annihilation operator. Why? Because it's a very strong, intense laser field, 10 to 18 photons. Remember that the process is very weak, 10 to the minus 7, 10 to the minus 8. So I need very intense fields to see something, to see anything. So I'm gonna consider that the laser field is it's in the same classical approximation, and I'm gonna, basically this is to say that the quantum fluctuations are so much smaller than the relative to the intensity that I can throw them away. Okay, so I do the calculations and I have the following terms. Okay, if I do the famous rotating wave approximation, which means that I throw away this is oscillating, right? This is a time-dependent Hamiltonian. If I throw away the terms that are oscillating a lot, and these are terms like, for example, this one times this one, it oscillates in omega L plus omega Q. Actually, this is a square, so 2 omega L plus omega Q, and so on and so forth. If I throw away every term that is oscillating a lot, and why can I do it? Because basically, if you remember perturbation theory, as long as I allow enough time for the whole system to understand all the oscillating frequencies, only the terms that are very close to resonance will have an impact, will have probabilities that are not negligible. That's why I can. So basically, unless I probe something in very, very small short times, and what do I mean by small short times? Times of the order of 1 over 2 omega L. Omega L is an optical frequency. It's 10 to 14. So imagine I have to, unless I probe things in times that are in this sort of scale, I can throw away the terms that are oscillating very fast, in principle, okay? Obviously, I can calculate corrections and so on, they won't be important here. So the terms that don't oscillate very fast, are the terms that we call close to resonance. For example, this will be in resonance if the photon of the laser is exactly the photon of the Stokes plus the vibration. And so this is a resonance, okay? So I only keep these terms, and this one is responsible for the Stokes process. So I create one photon Stokes, I create one vibration at the cost of converting one photon from the field. Yes, you asked me. Okay, thank you. Rephrasing the definition of the resonance. The resonance is going to happen whenever, for example, the frequency of the laser is equal to the frequency that I'm going to generate in Stokes plus one vibration, or the frequency that I'm generating in anti-Stokes minus one vibration.
With a tiny vibration.
Okay. Another way to say it is if I pump in green, that let's assume that my phonon is actually my photons are in, for example, if it's diamond, those are those are infrared photons. Okay. If I'm pumping green, I'm gonna see light in red more or less and blue. Okay. If I scan, the light in red corresponds to the conversion that gives one vibration to the crystal. The light in blue corresponds to the states. Okay, those two peaks will be the resonance. Okay, I still generate photons around the resonance. That's very important because I'm going to use them later. Okay, it's just that in those frequencies the process is much stronger. That's okay. So this is the moment in which I make this joke all the time because I love it. As always, this has been done in Russia many years ago. Okay, so the consideration of generation of photon pairs, correlated photon pairs, was done by Klitschko in the 1970s, and basically he discussed the possibility of the same vibration that is created by the Stokes process to be absorbed and creates the Stokes, which means that the two photons that are generated will be at least time correlated because they will share the same vibration. Okay, so this is one way of producing pairs of photons in this process, but like this is not the one that I'm interested in. I'm gonna go quickly here because those are some equations, but essentially what I'm showing here is that I will be interested actually in the what we call the virtual phonon exchange, and that means the following. So what you're seeing here is the frequency of bump, and there is one peak of resonance for water here. There are two resonance peaks here, and if I sit my detectors in these frequencies here and the analogous in this side, and I look for coincidence counts in these detectors, so I look for whenever one click and the other clicks at the same time, okay, I'm gonna pick up mostly pairs of photons that are generated by the process that Klitschko was talking about. However, these photons are dirty in the sense that their state is not pure. So they is not close to pure. So they don't display good entanglement. And why? Because there are phonons involved and so on and so forth. But if I displace my detectors a little bit, so instead of putting my detectors in frequency on top of a resonance, I put them close to the resonance, but not on top of it, the process that generates photons in this range of frequencies, a process that are straight in the generation of two photons at once. So I generate one Stokes and one anti-Stokes through the exchange of a virtual phonon. I never actually generate a phonon in the material. However, and this is very important for me in the end, the fact that there is a phonon that could be generated, or in other words, the fact that there is a vacuum of phonons there is going to be very important for me. So the fact that like I still somehow feel the presence of the resonance peaks, but only of the vacuum of the modes, okay? Of the phenomena. So I'm gonna skip these calculations, except that if I use this very, very hand wave phenomenological theory, that's already enough for us to figure out how the strength of the Stokes signal, the laser time width, the laser power, and the detector spectral position play a role on the probability of generating pairs of photons. So that's important because now, for example, we know that it grows with the power of the laser to the square. So if I concentrate more my pulses, if I generate more photons per pulse, I increase the chance. If on the other hand, I try to do it with continuous wave, in which the photons are very diluted in a very large coherence length, that the chance of generating pairs is very small because the power will be smaller. Okay? So things like that. Yes, Pierre.
So Marcelo, I'm going to shout because they're recording, but so you mentioned that it's not. So you said it's not pure and it's in resonance. And is it because of the thermal phone death, or is it because of the finite lifetime of the
No, it's not because of the thermal phonon bath, okay? Because those are infrared phonons. So at room temperature, well, if you plug their frequency for a diamond, for example, in room temperature there is from 10 to the minus 2 to 10 to the minus 3 thermal phonons, okay? And we see much, much worse purity loss than this. So it's more because you create the phonons and you may create a second Stokes field. So the chance that you're going to because the strength to create one Stokes field and an anti-Stokes is more or less the same as the chance to create two Stokes field.
Okay, so it's more like a multi-phonon event.
Exactly. Okay, that's the main source for it. Okay, so then you don't know anymore if the phonon that this anti-Stokes absorbed is the one that was created by the first Stokes process, but you understand, so it's because the signal gets much stronger. So you lose purity, okay? Fine. But this theory allowed us to predict so this is the correlation, Stokes and Stokes correlation. The blue curve is the one that comes from theory. The dots are the experimental points. It allowed us to predict the correlation curve as a function of the position of our detectors. The green here is the position of the Raman peaks, okay? The blue is the correlation function. And you see that it agrees quite well with the experimental points, except from this region here. So before the peak, it agrees well. After the peak, it doesn't. Here with diamonds, same stuff. We have good explanation for before the Raman peak, bad explanation for after the Raman peak. Our theory by then was symmetrical. We should get the same chance to form pairs of photons on both sides of my spectrum. If I place my detectors spectrally before or after the Raman peak, okay? And this is important because I'm going to explain why this happens, and this is the big thing of the result. So here what you see is, again, we are showing here that if in resonance, this is a pump and probe experiment that shows the existence of the phonon and the decay of the phonon. And off resonance, this is a pump and probe that shows that when you do it off resonance, there is no phonon in the game. Okay? So, again, we were probing time correlation, but we wanted to probe entanglement. So we did the experiment, and by we, I mean Aldo Jordan and his students in UFMG. I'm a theoretician, but like I always like to say that we did it, right? Because that allows me to give a talk about it. So we did the experiment in Minas Gerais, and this is the standard experiment for analyzing entanglement and polarization. You shine the laser here, you pump the crystal, the diamond is here in this position, so this is a microscope, and you then collect the laser here, and you throw and you show it some spectrometer. You then throw away you throw away the laser. There's a notch field here. Here, that's the notch. Then you're throwing a little bit of the Stokes to the spectrometer. Yes, and then you do analysis of the polarization of the photons by rotating these quarter wave plates and going through polarized beam splitters here and here. And this is the detection of the anti-Stokes, that's the detection of the Stokes, and this is the correlator. So basically, if this guy clicks at the same time as this guy clicks, you record a dot on your experiment. Otherwise, you don't. So that's the standard experiment, and I hear some echo. And when we do it for analyzing the polarizations, you see that so this graph here is showing H and H polarization, HV, VV, or actually, VV and VH. So you see that here I only have photons of V polarization. Then obviously they won't be polarized in polarization, entangled in polarization. Again, the same here, same here. Here I have a little bit of photons in HH polarization, pairs in HH polarization. And these two guys are the ones that are good candidates to display some entanglement in polarization. Why? Because when I collect photons in this configuration, I'm going to tell what I mean by configuration here in a couple of seconds, okay? Then there is a chance that I'm collecting photons of the same polarization, either H or V. And the entangled state, HH plus VV, if it is maximally entangled, should have the same probability of collecting a pair of H polarization and a pair of V polarization. So these are the two candidates for polarization. Who are these guys? So 1332 centimeters to -1 is the Raman frequency, the Raman resonance frequency for the diamond. So here it means that these two graphs is when I'm placing my detectors at exactly the Raman, the Stokes and Raman anti-Stokes frequency. So here I'm detecting the real phonon processes. So even though it seems like a good candidate for entanglement, I'm going to show in a couple of seconds that it's not. This is a mixture basically of states of HH and VV polarization, not an entangled state. So classically correlated, but not entangled. And here, what you see is at 900, which means that I have displaced my detector to closer to the laser field on both cases. So I'm a little bit closer to the laser field than the anti-Stokes. I'm a little bit closer to the laser field than the Stokes. So I'm not sitting on the resonance, I'm sitting close to the resonance. But inside the distance from the Stokes and anti-Stokes to the laser field. Okay? And this zero here means that I'm aligning my diamond to the polarization, so my crystallographic axis to the polarization of the laser, the pump laser. So this is the configuration that gives me the best chance for entanglement. Okay? Obviously, we tested all sorts of configurations. So I'm giving you the short result. And if we go in this and we try to reconstruct the state, that's the state that we get. And this state is 95% the phi plus entangled state and 5% the phi minus. So it's very entangled. If we did a violation of Bell's inequality, and Bell's, obviously, you violate if you go beyond 2, and the maximum is 2.8 something, so we're violating Bell's with 2.61. So it's certifiable that this is entangled, okay? So we found entangled states. But what's interesting about them? That's what I'm going to show from now on. The point is that, how are they entangled? Why are they entangled? And we had to solve this issue, okay? And we went through a large theoretical calculation to do it. And we had a hint, and the hint is because actually we have two processes that can generate photon pairs in this range of frequencies. One of them is the one that I've been describing for you for, I don't know, 20 minutes now. And the other one is standard, boring, old, electronic four-wave mix. Okay? Electronic four-wave mixing is like this. The material is transparent, so it means that, so in diamond, for example, the band gap is in ultraviolet. So I need to shine an ultraviolet photon, actually a large one, to excite my electron to the conduction band then. Okay? So I'm very far from this. So I'm very out of resonance of this process. However, the diamond, this electronic transition can still generate four-wave mixing for me, which means that it can convert two photons that are entering into two other photons that are whose frequencies sum up to the two that are entering. It's a very similar process to the one that I'm describing, but this one doesn't involve photons. This one doesn't involve vibrations of the material. And while it doesn't involve vibrations of the material, it has a different response. And the difference in response is what led us to our results. So I skipped some slides that I can come back. So we did a full quantum calculation. We did a full quantum broadband interaction, Hamiltonian. We did Heisenberg-Langevin equations for the phonons, taking into account the dissipation of the phonons. We included the two-photon wave function, so we restricted ourselves to the two-photon subspace. That's a technique that's very old and very widely used in spontaneous parametric down conversion. We used realistic pulse shapes. We included the filters of the detectors and so on. So we did a really full quantum calculation. And when you do it, taking into account that I can have electronic four-wave mix and generation of photon pairs from Raman processes, okay? The two-photon wave function we'll end up with this aspect where this is related to the spectral density of the laser. This is the response for the electronic four-wave mixing, and these are polarizations of the pump and the generated photons. So this is the tensor for the electronic four-wave mixing. And this is the response for the Raman. And you see that the main differences are, this includes the four-wave mixing tensor, chi-3 tensor, that relates the polarizations of the fields that are entering and generated. However, because I'm very far away from resonance, this doesn't depend on the frequency that I'm throwing basically. It's frequency dependent. On the other hand, this includes the tensor response related to the Raman process, which is different from the Raman, the four-wave mixing, the standard electronic four-wave mixing. But more than that, here the resonance is present, very present. Okay? So you see that this is the phonon frequency, this is the phonon line width, decay rate. And this is the frequency that I'm going to integrate. So I have these two components participating in the creation of photon pairs. This is the wave function related to two photons arriving on my detectors. This is a post-selected wave function, okay? And if I do the integrals here, I end up with a two-photon state that will have this aspect in which I have an amplitude of generating pairs of Stokes and anti-Stokes photons of V polarization, H polarization, and VH and HV. Okay, this is Stokes, this is anti-Stokes. Index E refers to electronic, index R to Raman. F is the integration of in frequency of this part here, and Y is the combination of these and these. Okay, YE for the electronic, YR for the Raman. Okay, and here is encoded the polarization of the laser field in respect to the crystallographic axis of my crystal. And here is just to show that, so if you put a Gaussian profile for the laser and you do the integrals, this is what you get for FE and for FR. Don't worry about this too much, except for the fact that FR depends on the tuning. So FR depends on how far away I am from the resonance, but also if the tuning is positive or negative. It changes the phase, it changes the sign. If I am to the right or to the left of my resonance peak, okay, it changes the sign. So, this change of sign is the one that explains the asymmetry in the probability of formation of pairs. What happens is that when I am on the left of my resonance peak, so when I put my detectors closer to the laser frequency, so inside the resonance peaks, I have a plus sign and I have constructive interference. I have a larger chance to form pairs. And when I put my detectors on the other side, the Raman signal, the Raman generation of pairs change signs and interferes destructively with the four-wave mixing, and I have a smaller chance to generate pairs. So that explains the asymmetry that we were seeing for a long time we couldn't explain. And what you're seeing here is experimental points and the curves obtained by the theoretical model. There's no fitting here, okay? There's nothing fitted here. We use all the experimental parameters, and that's enough for us to generate these curves. We extract the parameters from other data. Okay. like power, laser power, and laser line width, all this is extracted from a different set of data. We use these parameters here, there's no fit. So that's a very, very good agreement of the counts of SAS pairs as a function of the position of my detectors. So we trust this theory that we did enough to generate a kind of entanglement map. So now we can use this theory to predict how much entanglement we are going to get from Stokes anti-Stokes pairs as a function of the position of my detectors, as a function of the power of the laser, as a function of the line width of the laser, as a function of all the parameters that you can insert from the experiment. And so now we have a map that tells you how much, for example, where is the best point to get entangled pairs, what is the best spectral position, or if I don't get entangled pairs, where should I go, in terms of the alignment of the crystallographic axis, in terms of the spectral position of my detectors, in terms of the laser bandwidth, and so on and so forth. We can do this. So this string in the middle is the one that where the model doesn't work that well, because here we are doing the model for the virtual photons. This region in the middle is for real photons. So ignore this part in the middle, but apart from this, the rest of in here, the theory is good. It works well. And so the bottom line is, I did all this effort that is very tiring for you, certainly not for me. I can do this by heart, not for you. I did all this effort to conclude, to show you that, like, for the first time, at least to the best of my knowledge, which process indeterminacy lies at the core of the generation of entanglement. Why? Because I have two processes competing for the generation of photon pairs. I have electronic four-wave mixing, and I have Raman-related four-wave mixing. They generate pairs of photons that are different, both in their dependence with the frequency and their polarization. And the fact that I cannot say which process generated one particular pair. So in quantum mechanics, usually if there is no way in principle that I can say what's going to happen, what's happening, I have to assume a superposition. And that's what's happening here. I have a quantum superposition of the two processes, electronic and Raman-related generation of photon pairs. And it's, as far as I know, it's the first time that like a superposition of processes is used to generate photon pairs. And more important for us is that now we understand what's going on. So if we want to generate better entangled pairs, if we want to generate, anyway, have better control, we know where to push, we know what to make, like which kind of laser we need to throw, and so on and so forth. So that's very important for us. So I would like to conclude. Yeah, okay, I'm in time. Excellent. I'd like to conclude by saying that like this source has some advantages. One of them is that it's tunable in a long range. Why? Because I basically, as long as I'm within the transparency window, which is very large for lots of materials, I can shine. If I shine a red laser, I'm gonna get photon pairs a little bit to the yellow and maybe infrared. If I shine green, I get blue and red. If I shine blue, I get a little bit of close to ultraviolet or violet and green. So I can pick up my laser and change. If I change the frequency of the laser, I'm gonna get photon pairs, entangled photon pairs. And this is very difficult to get with parametric down conversion, because parametric down conversion converts one large photon into two smaller ones. So if I want visible photons, I have to pick up an ultraviolet laser for which the optics is crazy. If there are any experimentalists here working with ultraviolet lasers, they know what I'm talking about. Okay? It exists, it's expensive, it's bad usually. So if you can get visible light optics, better for you. It is also fine-tunable, because if I change my detector position a little bit, I get a different signal. I get different degrees of entanglement, I get different responses. And so I can control the degree of entanglement by rotating the crystal, for example. Any transparent material is enough for me. And if you guys think about any other advantage, please tell me, that I would love to increase the list here, okay? And these advantages, okay, it's still spontaneous, so I don't generate pairs on demand, okay? It's very not efficient. I have few pairs per pro, so increasing this efficiency is one of the things that we are now looking for, okay? And we don't have fully entangled pairs, but this is more a matter of maybe choosing better our materials. So we did it with diamonds, so but maybe we can look for materials that would give us closer to fully entangled pairs. Perspectives. So the perspectives are very high, okay? We are now involved in lots of collaborations that are going to start from now on, including ones with Unicamp, including Saint Pain, including other places as well, because we want to start using this to test materials, to look for better materials, to generate photon pairs, to use this to try to see if we can get information from the materials that you cannot get with the standard Raman spectroscopy, to test liquids and so on. We are starting collaborations with people from biology to do quantum biology, and I really mean it. Okay, quantum biology was something that was very hype 10 years ago, but it led nowhere. Okay, but now we are starting to get conditions to do real quantum biology experiments. So we are going to this direction as well. So these are good perspectives, including, for example, we have this project with a collaboration with UFMG and IDOR, which is called Quantum Vision. And we are trying to check the perception of quantum properties of light by humans. And we have postdocs, masters, and PhD students available there to look for it. We have a new INCT involving all these institutions to produce materials, to test materials, and so on and so forth. And we also have a brand new laboratory in Rio. We finally have the brand new laboratory. The older people here, unfortunately, they won't be able to make jokes about us anymore. They've done it for 30 years now, but now it's over. We do have a new building. Okay, it's working, it's there. The laboratory is beautiful. Gabriela, who is the leader, is finishing, setting it up. It's going to be a fantastic laboratory, full of new equipment, with excellent conditions. We are opening a Raman spectroscopy line there. We have a new position available, so we hope to hire even another type of physics as well. So we would like to have 3 types of experiments there, SPDC, Raman, and maybe something else. So that's very promising. And I cannot finish without acknowledging the people that have collaborated in this. So Ado is the leader of the Raman spectroscopy at UFMG. Wonken and me, we are the quantum opticians. Wonken is an experimentalist, but he is also a theoretician, so the theory has been done by the 2 of us. And Raul, who is the postdoc responsible for really doing the calculations, obviously. Right? I'm too old to do calculations. My job now is to find money, right? Apparently. That's all that I've been doing in the last, I don't know how many months. So. But, and Filomeno, Thiago, Diego, and Lucas are the ones that did the experiments in the last 10 years. So I think that's all I had to say. Thank you very much.
Thanks a lot. Questions? Perguntas?
Thanks for the talk, Marcelo. Due to the inelastic scattering, then these photons they get entangled to the photons as well. Does this affect your entanglement in the end?
No, so that's exactly the point. The pair of photons that are generated in resonance, okay, there's an entanglement swap, if you want. Okay, so first I have the generation of the Stokes and the phonon, and then I have the generation of the anti-Stokes from the phonon. So first I get some entanglement between the four-wave mixing and Stokes and phonon, and then that swaps to Stokes and anti-Stokes. However, the phonon decays in the middle, and I can generate more Stokes, and I can lose coherence due to this. But if I sit my detectors out of the resonance, okay, so basically the point is that even though I try to separate the two processes, everything is happening at the same time. But each one of them is very, very improbable. Okay? So most of the time I'm generating vacuum. Sometimes I generate a pair of photons. Okay? In which frequency? Any frequency that is possible, most probably in resonance. But if I put my detectors out of resonance and I collect a pair of photons there, these ones did not create a photon at any point. So they never get entangled with the vibrations of the crystal. However, the fact that the crystal can vibrate, there is a vacuum of phonon states there, influences the state of this pair of photons. So that's the trick. It's really a vacuum-induced effect in that sense. That's my way to explain it. If you talk to condensed physics, they will say that they exchanged a virtual phonon. They will say that the process is so fast that the phonon was created and absorbed within the time window. So that's another way to say the same.
In such a way that the frequency change was like from one photon to the other one.
No, so no.
Energy transfer.
I'm emitting two photons from the pump. One of them gets a higher frequency, the other gets a smaller frequency. But yes, it is induced by the vacuum of the photons.
Such a way that
But
no
like,
energy is
in condensed matter physics, we explain it in this way. Okay, it's a if you draw a Feynman diagram, that's the loop that you get. Okay, and this loop is in zero time. That's one way to explain it. Like, okay, if I do perturbation theory, then there's no phonon created, but the vacuum is there. The commutator of the operators that relates to the vacuum fluctuations is there in my calculations, in my perturbative calculations.
Marcelo, thanks for the talk. So in this sense that you're saying that you have a virtual phonon there, it means that if you do like a pulsed experiment, then you have like just one photon per pulse from the pump. You only see entanglement when the first and the second photon from the single photon pump are time correlated.
More than that, superposed.
so it's time.
So
Yeah. No, it's because time correlation, any time distance between them, I can, if I know the time
Exactly.
distance, I can
it
say
could
it's
be
time
just
correlated.
correlated.
I just need to change the
Exactly.
right, the electronic correlate.
Yes.
Because it's more than that, they have to be superposed.
No, so that's my question. They need to be superposed.
Yes, in that sense, yes.
So in that sense, how? So it is. There gotta be like a time scale here for the virtual phonon process there. If you go like to Chi3, which is like a 4-wave mixing, but this is not the time scale for the phonons.
This is exactly what you're asking.
Yeah, I know.
Okay? So
That's my doubt.
here, this is a pump and probe. experiment. So red is the optimized curve in terms of the time displaced between pump and probe if I want to optimize the generation of pairs. You see that it's slightly displaced from zero, and the reason is because I need to allow time for the pump to generate the Stokes and the phonon so that the probe eats the phonon and generates the Stokes. That's why it's slightly displaced from zero. The peak here is not at zero, it's displaced. And this is the decay time of the phonon. Obviously, if I allow the probe too much time, there won't be any phonon there to get. When I do it and I detect outside of the resonance, so I'm looking for pairs outside of resonance, the optimized pump and probe is when I throw them together, one on top of the other, and at zero delay.
No, I understand, but then why then it matters the alignment of the phone?
It doesn't. For the blue, it doesn't. What you're seeing here is the alignment of the laser, and it doesn't matter. So this blue curve is done. I didn't put here the line. Every line with here is at the same.
When your calculation, you have like everything was multiplied with the alignment of the phone. So you do have like a resonance, and you have like something that is like.
Sure.
So that's
So it does depend on the alignment of the phonon. Okay. If I'm doing it with a continuous wave laser, for example, that's very thin, then eventually it will depend on the alignment of the phonon, but only in terms of the probability response, not in terms of the best. Okay. So the point is that yes, the line width is there, but the laser is so much larger that when we calculate, the line width of the funnel doesn't play any, is not relevant for the off-resonance processes. Okay? Thank you for the question. And now I understood your question.
So can I ask another one?
You have to ask the audience, not me.
So about the temperature.
Sure.
So you were looking to the frequencies where, as you mentioned, like you are at the ground state for the phonons.
Yes.
So there's no thermal phonons there.
Yes.
What happened when you shoot down thermal phonons there?
It gets worse.
But you still have entanglement.
So the calculations with temperature are still in progress because they are hard. So Raul is finishing the calculations with.
But you have a feeling if there is still entanglement?
My feeling is that there will be some, for sure, especially in off-resonance. Okay? In principle, in off-resonance, it shouldn't make that much difference. Because, again, it's the vacuum fluctuations that matter, so they shouldn't make that much a difference. Obviously, if you heat it up too much, then you melt the material, then there is nothing going on. If you do it something intermediate, I expect that fluctuations the thermal fluctuations will make a difference. I do expect, especially because they will influence the other aspects of your experiment, but not necessarily this particular.
Tens of phonons is still good?
Tens
of phonons.
10 phonons, 12 phonons. I don't know. We need to do the calculations. Yeah, I don't know. Well, certainly one thing that happens is that it's going to make the line, the resonance larger, which means that for you to be out of resonance, you will have to move more and more, and at some point, you won't be able to get out of resonance, okay? So in that sense, if you have too many phonons, eventually the phonon line width may become much larger than the laser line width itself. Then you broaden too much your signal and you cannot get out of resonance. So, yeah, things like that. Okay.
So, if you understand correctly, your tensors for the four-way mixing and the Raman scattering need to be comparable, right?
The response.
For the entanglement to
Yeah.
work.
Yeah.
How lucky were you that you got a material that where this is comparable? I mean, is it common that they are in the same range? Or?
I'm certainly by far not the person to ask this question.
Yes, sir.
I'm a quantum optician.
Next time, ask.
I'm a lucky quantum optician if you want. Actually, to be fair, I'm not even lucky because the paper accepts whatever you want. So on paper, I say, I define they are of the same size. Then obviously it's up to the rest of people to find a material in which I'm correct. Okay. Luckily, yes, we did find some material in which it happens, but then you have to ask people that are not.
Yeah, but I mean, you only got this in diamonds or in water also you got entanglements?
No, we haven't tried in water, and I'm not sure we're gonna get entanglement from liquids, because the orientation of the molecules is random.
But you get that correlation dip when you cross the resonance, you get the dip for water as well.
Yeah. So yeah. So maybe
it looks like it's comparable.
No. But be careful. Be careful. Each molecule of water will have the same property of being able to generate pairs from electronic and Raman. Sure. But this is different from saying that I'll have polarization time. Because the probability to generate the pair is intrinsic to each molecule. So I expect the same destruction or construction interference for the probability of generating the pair. But now if this molecule generates HH plus VV in this direction, and this molecule generates what it considers HH and VV in this direction, the two disagree on what is HH and VV. And I don't know which one generated the pair, so I may get a mixture. So I expect that in liquids, I will have to orient the molecule somehow if I want to get them done. Okay?
Yeah.
That's my guess. This is one of the experiments that is in life. Eventually, they will do it. Okay?
Okay, thanks. Questions?
Marcelo, first talk. I've seen this topic coming over and over. Everybody was here when this PRL paper came out, right? And you guys certainly did a program on that. Right? You support so many aspects of it, so it's very nice to see the outcomes. My question is, so it seems to me that your description of being this really far off resonance is sort of saying, let's try to do parametric Raman scattering, right? In a way that, in the sense of parametric nonlinear optics, where you operate really far away from any electronic resonance so that you get the broad bandwidth that parametric nonlinear optics brings. You reduce the strength of the nonlinearity, but you gain in speed, for example. That's the sort of demonstration that you have in this very plot that is shown on the screen. But my question is, so assuming that that's the case, you had the slide where you compared the two sides of the resonance, and you can see the different interference. It seems to be sort of a funnel, let's call it a nonlinear funnel process, right? Where you're interfering the Raman nonlinear response around the Raman resonance with the broadband high tree nonlinearities. It's all over the place. It seems that there's just one major peak there, but for diamond at least, you should have different phonon modes that participate in the Raman scanning, right? So as you're scanning your laser, you're actually crossing different Raman modes, and you could eventually have multiple of this interference. Don't you see them in the lab? I mean, you're lucky on the diamond side, it has just one bright or one active Raman mode.
One optical phonon. In terms of frequency, yes. So yes, so if I have a molecule, for example, like water, in which I have 3 vibrational modes, or any other material that have more phonon modes, then what is inside the peaks for one will be necessarily outside the peaks for others. but the theory can take this into account as well, because they will be independent from rules. So theory can take, so basically what we will get is a three-term, for example, interference process. And by the way, when I say far away, it's not really, it's far in the sense that I'm not in the peak anymore. But it has to be close to the peak, otherwise the probability of having the Raman associated pairs goes to zero. Because it depends on the separation, the frequency separation. So I have to be outside the line width of the peak, the resonance peak, but not too far away. Okay, I have to be close to the peak. So it's parametric in the sense that yes, I leave the crystal in the way that it started, but it depends on the vacuum of the. You understand? It depends on the vacuum of the phone vibrations.
Okay, so we discussed on bringing this to the chip scale, right?
Yeah, sure.
The challenge here, I think, looking at your scales will be really the optical filters, because it's going to be operating at 10 in terms of terahertz, gigahertz scale. So I think that's what we need to think about on how we bring in optical filters that allow us to resolve this very narrow frequency band within optical, instead of optical phonon frequency range, acoustic phonon frequency range. But I think as an outlook, as you pointed, one thing that we're going to have available at these platforms is a very degree of control of the relative strengths between the acoustic response in that case and the nonlinear response. So we can probably play around with this interference strengths that we're seeing.
Yeah.
It's really exciting.
And regarding this, there was something that I wanted to discuss with you. Okay, and regarding this is because in the journal club that we do, a couple of weeks ago, the student presented a paper in which the guy was using a special technique, very smart technique to overcome exactly this problem. Because again, he was within the line width, so he didn't have resolution, but he created a smart technique. So obviously I don't remember the technique now, right? But I know about it, so it's one of those things that I know how to get the information. But I can ask the students to send me the paper, okay? So I'm gonna do it. I'm gonna send it to you guys if you haven't seen it yet, because I think it may be very interesting for you. Because I know you are looking for this, but you have the problem of falling within the line width. So, but they did exactly overcome this problem. So I'll send the paper to you. The other thing that your remark is something that I wanted to say and I forgot. Is that exactly, like one of the things that made me more proud about this is that this is almost 100% Brazilian research. Theory and experiments done in Brazil. There are a few papers with external collaborators, which I think is great. Obviously, I'm not saying that we shouldn't. I actually think that we should collaborate with people from all over the place. But at the same time, it's nice to have a line of research that was open here. Nowadays, you have people in other places trying to replicate results and do other things with this. And where you have experiments in, theory done in Brazil. Okay, so that's something that makes me very, very happy about this.
Next thing, Marcelo.
And by the way, for the students here, another remark, which is that this is one case in which theory and experiments, we had no idea what we were going to get. And experiments were showing some results, theory had to try to follow. And then theory was expecting some results, and experiment had to follow. So we really exchanged this for 10 years now. So that's great.